For more videos like this for Discrete 1, you can check out Sarai's studies. Link is in the description box below. Today we're going to talk about operations on sets, or what Hamidi likes to call set algebra. The first operation is what we call the complement of a set. Complement means opposite. You're just finding everything that's not in that set. So let's say you have a set A and you want to find the complement of that set. There's 3 different ways to denote that. You can say A bar, A prime, or A C. So C for complement. And the idea is, in the universe of all things, of all elements that are under consideration, we'll have a set A. So this is our set A. And the complement of set A, as I said, complement means opposites, everything that's not in A. So if this is A, the complement of A is literally everything outside of A, which goes to show the importance of a universal set. Because if we didn't have a universal set, we would just have set A and we wouldn't know the opposite of A. We wouldn't know what's outside of A in the first place. So you always, especially if you're in Hamidi's class, have to draw the universal set. When Garcia gave this lecture, he did not draw the universal set. He did it for the complement because you need it, but for the other operations, it was kind of common sense. Everybody knows it's there, so he didn't draw it, but Hamidi does take points off if you don't draw it. So let's do an actual example. If the universe of all of the things that we are considering, all of the elements that we are considering, is just made up of the numbers 1 to 10, so in the universe, we're just considering the numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. These are all of the numbers in the universe of all things we're considering, of all elements we're considering, of all numbers we're considering. And out of all of these numbers, set A contains the numbers 1, 2, 3, and 4. So this is set A. And if we're trying to find the complement of set A, well, if this is set A, the complement is everything that's not in A. So basically everything outside of A. So we would say that the complement of A is equal to the set containing all the numbers we just highlighted. So 5, 6, 7, 8, 9, and 10. And if you didn't use the Venn diagram and you were just looking at the sets, well, to find the complement of A, it's basically everything in the universe, everything in this box that's not here. So if 1 is an A, you wouldn't include 1. If 2 is an A, you wouldn't include 2. If 3 is an A, you don't include 3. If 4 is an A, you don't include 4. So everything else that's left, that is the complement of A, which is what you see here. Now, if you have Hamidi, if she asks you to find the complement of a set, even if you use a Venn diagram, or even if you just do it in your mind by looking at the sets, if you just give this as an answer, she won't give you points because you have to show your work. And the way you show your work is by writing down really what we're doing in a formula. So the formula is that the complement of set A is equal to the universe of all elements we're considering minus all of the elements in A. In other words, all of the elements in this entire box, in this entire set, that are not, minus for not, in A. So even though this becomes really common sense after you're done with Discrete 1 and you're taking Discrete 2, Hamidi still wants you to write this down on your exams or your quizzes to show your work, so keep that in mind. Now, using the Venn diagram, we can come up with a formal definition for the complement of A, which you do need to know for your proofs. So we say that the complement of A is going to be equal to the set, and if you call all of your elements X, so you just say any element is just X, we could say any element X such that, and what's the condition that X has to satisfy? Well, the condition is that it can't be an A. So X is not an element of A, and that's it. That is the set builder notation for the complement of A, and you can use your Venn diagrams to tell you exactly what to write. If these are all X's, if these are all of my elements, then the complement of A should only be X's that are not inside this circle. So I don't include any of these right here. I only include all of these, which is what I did. So this is an example of an operation that you can perform on one set only. There are more like the power set, the Cartesian product, but I have 2 separate videos on those. The second operation is the union between sets. So let's say I only have sets A and B, then to denote the union between sets A and B, it's simply A union B. So U for union. That way you'll never forget. Now, if you want the union between 2 sets, think of what a union is in terms of the workforce. It's when employees come together, they're joined together to fight for a cause. But the point is that the union between 2 sets is going to be the set containing all of the elements in both sets together. So all of the elements in A and all of the elements in B are coming together in one set. So forget about the numbers for now. If you just have a universal set, in that universal set, some of the elements are in set A, and some of the elements are in set B, and some might be in both A and B. The union of sets A and B, again, contains everything in A and everything in B. So that means everything in this circle and everything in this circle, and that's your Venn diagram. So just from that, you can come up with a set builder notation. that the union between two sets is going to contain all elements x such that those x's, these x's that I'm highlighting, have to be in A, so the x has to be in A, or it has to be in B. So or x has to be in B. And the way to remember it's an or is that this looks like our or symbol from propositional logic. Just remove the curves and it becomes our or symbol. Now as for a numerical example, again, if the universe of all elements I'm considering are the numbers 1 to 10, then my box here is going to contain the numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And out of all of these numbers in the universe right here, my set A is going to contain the numbers 1, 2, 3, and 4. So this is my set A. And my set B is going to contain the numbers 1, 5, 8, and 3. So set B is going to be this set right here, 1, 5, 8, and 3. So then again, you just look at this, the union of A and B. Think of all of the elements coming together from A and B. So you want to highlight A, all of the elements in A, and you also want to highlight all of the elements in B. So then at the end of the day, union B is going to be equal to the set of all of the elements we just highlighted. So we have 1, 2, 3, 4, 5, and 8. And if you're just looking at the sets and not using the Venn diagram, we'll define the union of sets A and B. Well, remember, union means all elements from both sets joined together in a union. So it's just going to be the set containing all of the elements in A and all of the elements in B. So I see 1 here, put it there. 2, put it there. 3, put it there. 4, I put it there. Now here's what you have to keep in mind. I see 1 here. I'm not going to add it because I already have 1 here. Remember that sets only contain unique elements, so you cannot do duplicates. I see 5. So I put it here. I see 8, so I put it here. And that's it, because 3 I already have in my set. I can't put it in again. And this is exactly what we see right over here. The third operation that we can perform on sets is the intersection between sets. If we're just dealing with two sets, we denote the intersection between, let's say, sets A and B as A intersection B. If you remember this, U for union, then you'll know that the opposite symbol is just going to be the intersection operation. So again, in the universe of all things we're considering, all elements we're considering, forget about the numbers, we have sets A and B. So this is set A, and this is set B. The intersection of sets A and B, it's literally in the name. You're taking the intersection of what they both have in common. Both of these sets intersect right over here. So you just shade in that area. And then from the Venn diagram, it's easy to get the formal definition of the intersection between two sets. And that is that it's going to be made up of all elements x, such that, and then what's the condition? So these are all of our x's. Where are these x's? Well, they have to be in A, and they have to be in B at the same time. So x has to be an element of set A, and x has to be an element of set B. And it's way easy to remember because look at the symbol. This looks like the and symbol, just like this looked like the or symbol from propositional logic. So this symbol should remind you it's and. Now just to note, Hamidi actually writes or here and writes and here. She says that it's not really common to use the propositional logic symbols in set builder notation, but she didn't say it's incorrect. She just said it's not common, so you could still use them. However, Garcia is absolutely fine with you using these symbols. If I'm trying to find the intersection between sets A and B, you can read it as you read a proposition. In order for the value to be in the set, it has to be in A and in B. So think of this as an and. Or just remember, intersection means what they both have in common. So if you're looking just at the sets, what do they both have in common? Well, they have a 1 in common, and they have a 3 in common. They don't have 2, 4, 5, or 8 in common, so it's really just 1 and 3. If we're doing it using a Venn diagram, well, again, it's the same story. Out of the universe of all elements we're considering, those elements are 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Set A contains the elements 1, 2, 3, and 4. So this is set A, and set B contains the elements 1, 5, 8, and 3. So that is set B. And again, the intersection is what they have in common, where both sets intersect right over here, and that gives you your answer. So your set should only contain 1 and 3, which is what we have here. And finally, the last operation is the difference between sets. So if we're just dealing with two sets, A and B, then we can denote that as A minus B or B minus A. Now this notation is easy to remember because difference, you can just think subtraction. And the way you read it is really easy. It's everything that's in the first set, so everything that's in A, except if it's in B, right? You're just taking away everything that's in B. So when you have a difference problem, your answer always is going to start with the first set. So the first set is A, so it's just going to be the set containing 1, 2, 3, and 4. And then you just subtract anything that's also an element in B. So do I see 1 in B? Yes. So I remove that 1. Do I see 2 in B? No. Do I see 3 in B? Yes, I do. So I remove that 3 from A. Do I see 4 in B? No, so that's fine. In other words, the elements in my set are just 2 and 4. So it's everything that is in set A, but that wasn't in B, which should make sense. We have a negative on B. We don't want anything from B. So in the universe of all elements we're considering, if we have a set A and we have a set B, then the difference between A and B graphically is everything in A, so this entire circle you would highlight, except if it's in B. So everything in A that's also in B is this region right here, so we don't want to highlight that region. In other words, we only highlight this part, everything that's in A and not in B, so we do not highlight this region here. So just by looking at this, we can say that the difference between two sets in set builder notation is going to be equal to all of the elements X, so this is X, such that, and then what condition does it satisfy? Well, it's definitely going to be in A, so X should be an element of A, but it cannot be anywhere in B. So, and X cannot be in B. And that would be your formal definition for the difference between two sets. And if we want to answer this question using a Venn diagram, well, we already know that the difference is you highlight the first set that they give you, which is set A, so everything in this set, except if it's in B. So nothing from this set. So we basically have to remove all of this, so it just leaves us with this little part right here. And so that leaves you with just the elements 2 and 4, which is exactly what we see right over here. And so these are our 4 operations. These operations are the ones that we can perform on multiple sets. So not just 2 sets, we can do A, union B, union C, union D, and so on. And this is the one operation we covered that we could only perform on one set.